Hello friends. Today we are going to take a look at the compact ALLPOWERS VOLIX P300 portable power station. Inside, there is a lithium iron phosphate battery with an energy capacity of 256 watt-hours, a 300-watt inverter, and a claimed pure sine wave output. The station can also charge from the mains at up to 300 watts. But we are not going to simply list the specifications. It is much more interesting to see what all of this actually delivers in practice. So we will test the inverter's real output power and see what happens as we approach the claimed 300 watts and when the station is overloaded. We will use an oscilloscope to examine the output voltage waveform and also find out how much energy can actually be obtained from the battery through the AC output. We will also separately test USB Type-C, laptop charging, and UPS mode with an actual mains power outage. We will go through all of this in more detail in a moment. But first, as usual, I would like to ask you to like this video so that more people who are interested in this topic can find it, and subscribe to my channel if you have not done so already. The VOLIX P300 comes in an ordinary cardboard box without any kind of premium packaging. In terms of its format, this is a compact portable power station, a backup power source for electronics and small household appliances, and it is not intended for high-power loads. The package is also minimalist. The station itself, a mains cable, the manual, and documentation. There is no external power adapter here. The mains charger is built directly into the housing, so an ordinary cable is enough for charging. Automotive and solar cables are not included in the standard package. At the time of filming, the VOLIX P300 costs less than comparable compact models from EcoFlow and Bluetti. I have left links to the official website and the ALLPOWERS store on AliExpress in the description. The difference is not huge, though, so it is especially interesting to find out whether the lower price has affected the device's real-world performance. The station itself is fairly small and weighs around 3.5 kilograms. In other words, it can easily be carried with one hand, placed near a desk or router, or taken with you. There is a folding handle on top, which retracts almost completely into the housing when not in use. Most of the connectors are located on the front, while the charging inputs are positioned on the side. There is a standard mains connector here, so no special adapters are required for charging from 230 volts. Next to it is a separate input for connecting a solar panel or a vehicle electrical system, with an input voltage range of 11 to 30 volts. The front panel is designed quite simply and logically. There is one 230-volt AC outlet, two USB-A ports rated at up to 18 watts, USB Type-C rated at up to 100 watts, and a separate 12-volt output. AC and DC have their own dedicated buttons, so converters that are not needed can be switched off independently of each other. The 12-volt output is implemented as a standard automotive socket and is covered by a rubber cap. It is rated for a load of up to 10 amps, or 120 watts. This output can be useful for automotive electronics, small refrigerators, routers connected through a DC converter, and other devices where it makes no sense to first convert the battery's energy into 230 volts. And in the center, there is a fairly large information display. It shows the battery charge percentage, input and output power, active outputs, fan operation, and the estimated time remaining until the battery is fully charged or discharged. Now we can move directly to the tests. But before checking the charging speed, the station needs to be discharged to a fairly low level, which is what it is currently doing under a small load. And while it is discharging, let us take a look at the ALLPOWERS app, because it provides access to several important settings that we will need later. The VOLIX P300 is equipped with Bluetooth. To activate it, you need to hold down the left DC output control button for about 3 seconds. After that, the Bluetooth icon appears on the station's display, and the device becomes available for connection in the app. During discharge, the station's active cooling system switches on periodically. The fan is located on one of the sides and does not run continuously. The higher the load, the more often it switches on and the longer it runs. At low power, the station remains almost silent for a significant part of the time. While the station is discharging, we can also measure the noise level. For this, I used one of the Android apps with fairly good reviews. On the left, we can see the background noise level in a room where no equipment is running, around 42 decibels. I was unable to get it any quieter in my apartment. With the fan running, At a distance of about 1 meter from the station, we get around 55 decibels. The app itself compares this level to a quiet office room. And if the smartphone microphone is placed almost directly against the ventilation grill, the reading rises to approximately 86.4 decibels. That is already quite noticeable noise, but in actual use, of course, nobody is going to stay that close to the fan. After Bluetooth is activated, the station is detected by the app almost immediately and can be added without any complicated setup. The main screen displays the current battery charge, estimated operating time, input power, and output power. From here, you can also remotely switch the AC and DC outputs on or off, and choose an AC frequency of 50 or 60 Hz. For our upcoming tests, the settings section is the most interesting part. There are 3 operating modes in the settings: mute, standard, and fast. These are essentially the modes whose effect on power and mains charging speed we are now going to test in practice. There is also an eco mode with automatic shutdown under a small load, and its activation time can be set to 1, 2, 4, or 6 hours. The remaining settings are minimal. You can change the device name and view its system information. We will not spend too much time on the app and will move directly to the charging test. We will test all 3 available modes one by one. First mute, then standard, and finally fast. The station has been discharged in advance to 14%, which is low enough that the system should not yet be limiting charging power due to approaching the upper charge threshold. We start with mute mode. After it is activated, a crossed-out speaker icon appears in the upper left corner of the display. The station itself shows an input power of around 109 watts, while a household power meter on the main side shows just over 115 watts. During my observation in this mode, I did not notice the fan switching on, which is entirely consistent with the purpose of the mode. Charging is noticeably slower, but almost silent. The next mode is standard, which was enabled by default. There is no separate mode icon on the display here. According to the station itself, the input power rises to around 268 watts, while the power meter shows almost 275 watts being drawn from the mains. Cooling now switches on periodically, but the fan does not run continuously. And finally, fast mode. After it is enabled, a battery icon with a lightning bolt appears at the top of the display, and the fan starts almost immediately. The station now shows around 318 watts of input power, while the household power meter records approximately 324 watts. So the difference between the 3 modes turned out to be quite real and fairly significant. Maximum power is not maintained until the very end of the charging process. As the battery approaches 100%, the charge controller gradually reduces the power. For example, at 93%, the station is already accepting only around 104 watts, while the power meter on the outlet side shows approximately 117 watts. This is normal battery charging behavior. Most of the time is saved during the first, fastest part of the process, while the final percentages are charged much more gently. In the end, charging from 14 to 100% in standard mode took a little over an hour. After reaching 100%, the station itself already shows 0 watts at the input, which means the main charging process is complete. At the same time, the household power meter still records a small amount of mains consumption, around 3 watts. Most likely, this is the electronic's own power consumption while the battery is fully charged. That concludes the charging test. The battery is now fully charged, and we can move on to the reverse test. Let us see how much energy the station can actually deliver through the AC output. For this test, I connect the fully charged station to a constant load of approximately 180 watts through an external power meter, which will measure both instantaneous power and the amount of energy delivered. Before starting, the counter is reset to 0. We switch on the inverter and begin discharging the station. Now we simply need to wait until the station shuts down completely and then check the final value in kilowatt hours. The first intermediate measurement is taken after 18.5 minutes. The display shows 75% charge remaining. The load has not changed and is still 188 watts, and the estimated remaining operating time is approximately 55 minutes. By this point, the external power meter has recorded 55 watt-hours of energy actually delivered through the AC output. So far, the readings look perfectly reasonable, and we continue discharging without changing the load. The second intermediate measurement. With 49% charge remaining, the station continues to operate steadily with the same load of around 190 watts, while the estimated remaining operating time is approximately 34 minutes. By this point, the external power meter has recorded 116 watt-hours of energy actually delivered. So far, the discharge is progressing smoothly without any noticeable deviations. Another intermediate measurement, and this time we will also compare the power readings. With 27% charge remaining, the station shows a load of around 191 watts, while the external power meter records approximately 186.5 watts. The difference is small, which means the station's own readings are quite close to the actual power consumption of the load. At almost the same point in the discharge cycle, with 26% remaining, we now look at the accumulated energy. The external power meter has recorded 164 watt-hours delivered through the AC output. We continue discharging until the station shuts down completely. The final stage of the discharge turned out to be quite interesting. Immediately before shutting down, the station still shows 6% charge remaining and continues supplying around 190 watts. By this point, the external power meter has recorded 218 watt-hours of energy actually delivered through the AC output. After that, the inverter switches off and the load disappears, but the station itself remains powered on and still shows 5% charge. In other words, it does not allow the AC output to discharge the battery all the way to the displayed zero level, leaving a small reserve. If we compare the 218 watt-hours obtained with the stated battery capacity of 256 watt-hours, we managed to get approximately 85% of the nominal energy through the AC outlet. For an AC output, this is a very respectable result, since it already includes the inverter's own losses and the small reserve that the system keeps in the battery. Now we move on to testing the inverter's power output and the shape of its output voltage waveform. An oscilloscope is connected to the station's output, and I will gradually increase the load while monitoring the readings on the station's own display. Before the AC output is switched on, the oscilloscope naturally shows a flat line. We switch on the inverter, connect an initial load of around 50 watts, and get a stable sine wave at a frequency of 50 Hz. Then we gradually increase the power. The station operates confidently first with a load of around 166 watts. Then around 244 watts. And after that reaches the claimed 300 watts. What is more, it also handles around 335 watts without any problem, so there is indeed a small overload margin. At the same time, throughout the entire tested range, the waveform remains close to a proper sine wave, with no obvious distortion visible. When attempting to increase the load even further, the protection system activates. The station switches off the output, the screen goes dark, and then it powers on again with an overload indication. A warning icon appears together with error E2. So in practice, the inverter is not strictly limited to exactly 300 watts. It allows a small margin of around 10% and only then enters protection mode. Now let us test USB Type-C, which is rated for up to 100 watts. First, I connect a specialized USB tester and check the supported fast charging protocols. It detects support for Power Delivery 3.0, as well as a whole range of additional protocols, including Quick Charge, Samsung AFC, and Huawei FCP/SCP. So in terms of compatibility, the Type-C port appears to be quite versatile. Now let us test it with a real load. For this, I partially discharged the laptop battery in advance so that, through Type-C, the station would not simply keep the computer running, but would also actively charge its battery at the same time. In this mode, the station shows an output power of around 96 watts. So the claimed 100 watts through USB Type-C are practically achieved here, and for most modern laptops this amount of power is more than enough. By the way, powering a laptop directly through Type-C is usually more efficient than using its mains power adapter from the station's AC outlet, because this eliminates an additional conversion stage through the inverter. Now let us test UPS mode. As a sensitive load, I use a Beelink mini PC connected directly to the station's AC output. From the laptop, I start a continuous ping to this computer, so even a brief loss of power should become visible through dropped packets. I disconnect the external power supply, forcing the station to switch from mains power to the battery, and then restore the mains power. I repeat the test. In both cases, the mini PC continues to operate, and not a single ping packet is lost throughout the entire test. So with this specific load, UPS mode worked successfully. Switching to the inverter and back was fast enough that the computer did not notice it at all. After several hours of continuous operation in pass-through mode, I repeat the test, but this time I add an oscilloscope. The Beelink mini PC has remained connected to the AC output of the VOLIX P300 the entire time, while a continuous ping is still running from the laptop. I disconnect the station's external power supply. The VOLIX switches to battery power. The sine wave remains visible on the oscilloscope, and the ping does not lose a single packet. I restore mains power. Now we wait at least half a minute and repeat the cycle once again. The result is the same. The mini PC survives the switch to battery power and back without rebooting and without losing the connection. And as a control test, I manually switch off the station's AC output. A flat line immediately appears on the oscilloscope, and the ping disappears at once. This proves that the test is genuine. And now we can sum everything up. The ALLPOWERS VOLIX P300 turned out to be a quite interesting compact portable power station. Of course, with a capacity of 256 watt-hours and a 300-watt inverter, this is not a solution for powering high-power household appliances. Its intended use is for a laptop, router and network equipment, a small computer, lighting, charging gadgets, and other relatively low-power electronics. At the same time, my unit confirmed the main stated specifications. Through the AC output, I managed to obtain 218 watt-hours, which is around 85% of the battery's nominal capacity when inverter losses and the reserve retained by the system are taken into account. The inverter handles the claimed 300 watts properly and even has a small margin. The station continued operating at around 335 watts, and when the load was increased further, the protection system activated correctly. The output voltage waveform remained close to a normal sine wave throughout the entire tested range. USB Type-C also proved to be fully capable. With a partially discharged laptop, I obtained around 96 watts of actual power. This is especially convenient for such a use case because you can avoid using the laptop's mains power adapter and eliminate the extra conversion through the AC inverter. I also like the charging options for the station itself. There are 3 modes: a quiet mode at around 110 watts, a standard mode at around 270 watts, and a fast mode in which the power exceeds 300 watts at the beginning of charging. So you can choose between charging speed and noise level. I also tested UPS mode separately. First, immediately after connection, and then again after several hours of continuous operation in pass-through mode. In both cases, the Beelink Mini PC handled the mains power outage and restoration without rebooting and even without losing any ping packets. On my unit, I did not encounter any problems with extended operation in this mode. Overall, I would consider the Volix P300 primarily as a compact backup power source for low-power electronics. It is small, charges quickly, has a 100-watt Type-C port, a lithium iron phosphate battery, and a properly functioning UPS mode. And considering that it costs somewhat less than comparable compact models from better-known brands, it turned out to be quite a competitive option. That is all for now. I hope the video was useful and interesting for you. I would appreciate your likes. They help promote the video on YouTube. If you do not want to miss new reviews and smart home tutorials, subscribe to the channel. You will find all the mentioned links, as well as my Telegram channels, social networks, and discussion groups in the description below the video. Thank you for watching. See you next time. Peace to everyone.